from California University of Pennsylvania.
Hi everyone, my name is Natalie Hilbert. I'm from CalU, and the title of my talk is Fibonacci in Fusion. And pretty much what I'm going to discuss is me and my friend Michael Kubitek, we worked jointly on proving a proof. So here's the overview for it. I'm going to talk about the preliminaries first. I'll explain what the Fibonacci numbers are in the sequence. Then I'll tell you why they're important. And then I'll talk about the Fibonacci association, and they produce the Fibonacci quarterly. Then I'll get into my actual research problem. I'll show you the proposed problem, the preliminaries, which are the theorems and definitions I used to solve it, and then I'll explain my proof. And then conclusion, I'll tell you what I did with the proof, and then our future endeavors. So the Fibonacci sequence, it starts off with numbers 1 and 1. In order to obtain the next number in the sequence, you add the previous two terms. So 1 plus 1 would be 2, then 1 plus 2 is 3, and the sequence continues. Then we have 5, 8, 13, 21, 34, and 55, etc. So a more formal definition of this would be that f of 1 is equal to 1, f of 2 is equal to 1. Then we have f sub n is equal to f sub n minus 1 plus f sub n minus 2 for every n greater than or equal to 3. So you might be wondering why these are important. Well, they occur in nature. If we look at the number of petals and flowers, the number of petals represent a Fibonacci number. So in the first picture, the number of petals, there are 3. The next one has 5. The next 3 have 13, and the last one has 8. 3, 5, 8, and 13 are all numbers in the Fibonacci sequence. Another way they're in nature is in the number of pairs of rabbits. If we start with 1 male and 1 female rabbit, after a year from breeding, the number of pairs of rabbits in the year will be a Fibonacci number. And if we look at the month-to-month ratio, those are also pairs, or the numbers in the Fibonacci sequence. So at the end of the first month, we have 1 pair. At the end of the second month, we have 1 pair. At the end of 3 months, we have 2 pairs. Then we have 3 pairs and 5 pairs. This is also the original problem that Fibonacci himself explored. In order to develop the sequence, he looked at the number of pairs of rabbits in a year. They're also found in many areas, such as biology with the rabbits and the nature, combinatorics, formal languages, and many more. So the Fibonacci association was incorporated in 1963. It focused on Fibonacci numbers, related mathematics, and it emphasized new results, research proposals, challenging problems, and new proofs and ideas. Mathematicians and professionals will submit articles to this, and so this is of the website. So then they developed the Fibonacci Quarterly, which is an academic journal that is submitted 4 times a year, so it's quarterly. And mathematicians and professionals can submit articles with well-developed references. And along with that, they can also submit problems that people can prove. And these problems aren't just meant for professionals, undergraduates can solve them too. So this is the actual problem that we worked into solving. It is from the May 2013 issue. This is what they put into the Fibonacci journal. And we had to prove these 2 inequalities. The L sub n is Lucas numbers, and the Lucas numbers follow the same sequence of Fibonacci, where you add the 2 previous terms, except they start with 1 and 3 instead of 1 and 1. And the F is for Fibonacci. So we had to prove both of these inequalities. So in order to do so, we had to use some theorems and definitions. So the first definition we used was the definition for a generalized Fibonacci sequence, which is denoted G sub n. And it's with integers a and b, and it's defined reclusively by G sub 1 is equal to a, G sub 2 is equal to b, then G sub n is equal to G minus 1 plus G sub n minus 2 for all n greater than or equal to 3. And as you can see, this is the same as with the Fibonacci sequence, where you add the 2 previous terms to obtain the next number in the sequence. So if we look at the first 8 terms in the generalized Fibonacci sequence, we have G sub 1 is equal to a, G sub 2 is equal to b, G sub 3 is a plus b, G sub 4 is a plus 2b, G sub 5 is 2a plus 3b, G sub 6 is 3a plus 5b, G sub 7 is 5a plus 8b, and G sub 8 is 8a plus 13b. If we look at this chart where we're comparing the generalized Fibonacci that they follow the same pattern of where you obtain the next number of the sequence by adding the previous two terms. Another useful definition is the use of the constant mu. Mu is equal to a squared plus ab minus b squared, and this occurs in many of the formulas for the generalized Fibonacci numbers and is a characteristic of the generalized Fibonacci sequence. And you'll see where it's used later on. One theorem we used was the Cauchy-Schwarz inequality, and this is let x sub 1, x sub 2 all the way to x sub n, and y sub 1, y sub 2 all the way to y sub n be real numbers. Then we have the inequality of the summation of I equals 1 to n x sub I times y sub 1 quantity squared is less than or equal to the summation of I equals 1 to n x sub I squared times the summation of I equals 1 to n y sub I squared. There are many identities with the generalized Fibonacci numbers. So one identity is the summation of I equals 1 to n, g sub I is equal to g sub n plus 2 minus b. The second identity is the summation of I equals 1 to n, g sub I squared is equal to g sub n times g sub n plus 1 plus a times the quantity of a minus b. And the third identity is g sub n squared plus g sub n plus 1 squared is equal to the quantity of 3a minus b times g sub 2n plus 1 minus mu times f of 2n plus 1. So now we're going to actually get into the proof. So here was the original problem that we had. So what we did is that we ended up proving a more generalized statement, and by proving this more generalized statement, we include infinitely many inequalities and not just the two that we originally proved. So the more general statement that we proved is that we have 2 times the quantity of gn plus 2 minus b squared is less than or equal to the quantity of 3a minus b times g sub 2n plus 1 minus mu times f of 2n plus 1 plus 2a times the quantity a minus b all multiplied by n. So, if we look at the left-hand side of our equation, we started with 2 times the quantity of gn plus 2 minus b squared. And that is equal to, using theorem part 1, 2 times the quantity of the summation of I equals 1 to n, g sub I, and that quantity squared. We can say that g sub I is equal to multiplying itself times 1, because anything times itself is still that same number. Then if we do that, we can use the Cauchy-Schwarz inequality. So we have to substitute in, and we can say 2 times the quantity of summation of I equals 1 to n, g sub I squared times the summation of I equals 1 to n, 1 squared. And we know that's less than or equal to what we started with because of the Cauchy-Schwarz inequality. The summation where I equals 1 to n, 1 squared is equivalent to n, which is where the n is on the right. So in order to go to the next line, we can bring the n to the front, just rearranging. And then using theorem part 2, g sub I squared, that is equivalent to g sub n times g sub n plus 1 plus a times the quantity of a minus b. So we know that we can say that is less than or equal to n times the quantity of gn squared plus gn plus 1 squared plus 2a times the quantity of a minus b, and that's because 2a is always less than or equal to a squared plus b squared. Then if we use theorem part 3, we can substitute the g sub n squared plus g sub n plus 1 squared as 3a minus b times g sub 2n plus 1 minus mu times f of 2n plus 1, and then the rest of it. So if we were to go back and we were to look at what we proved, by sequencing the equalities and inequalities, we proved our generalized statement we started with. And then in order to obtain the two inequalities they started to prove with, we can use, for the first one where it's 2 times f sub n plus 2 minus 1 squared is less than or equal to n f sub n 2n plus 1. If we set a equal to 1 and b equal to 1 in our generalized Fibonacci sequence, we will obtain that inequality. Then with the other one, which is 2 times the quantity of n, L sub n plus 2 minus 3 squared is less than or equal to 5 f sub 2n plus 1 minus 4 times n. If we set a equal to 1 and b equal to 3 in our generalized Fibonacci sequence, we will obtain that inequality. So this proved our result. So what happened now is in November 2013, we submitted our proof, and it is currently under review right now. It is anonymously reviewed by professional mathematicians, and they will, after reviewing everything, they will choose one original proof to be highlighted in their quarterly, and all other people that submitted correct solutions will be mentioned in the quarterly too. So for future, in May 2014, the publication of the journal will be released with this solution to our inequality in it. So fingers crossed that we get published. And then we plan to submit more proofs. We actually submitted another proof, and Mike will be talking about that later. So I have actually handouts with our inequalities and our actual proof if people would like copies of it so they can